So here we'll try to wrap up the 2004 AB free response question number 4. Didn't get a chance to do part C in the last video, so if you want to see parts A and B, just go and check the other video that I have on this particular problem. But in part A, what we did was we took the first derivative and we showed what the first derivative was equal to, but immediately after differentiating on both sides with respect to x, we had this line. Now what I'm going to do is I'm going to just kind of clean this line up a little bit, make it look a little bit nicer. So I'm just going to get rid of some of the grouping symbols and some of the exponents that I don't necessarily need to show. So the 0 I don't need to show, and then I'm going to distribute my 3 in over here. So I'm looking at 3y and then plus 3x dy dx. What we want to do in part C is we want to find the value of the second derivative at point P found in part B. So from part B, we found that we had a horizontal tangent line at the x value of 3 and the y value of 2 on this curve. Before we get to the second question that's asked here, we're going to have to find the value of the second derivative. And we haven't taken a ton of second derivatives implicitly. If you want to take the second derivative implicitly, what's typically easiest to do is to just differentiate this equation, so it's not solved for dy dx, but just take the derivative of this equation with respect to x on both sides. So that's why I copied this into this onto the screen from part A. I want to take the derivative of both sides of this equation with respect to x. And when I take the derivative of this piece of the first derivative, I'm going to generate a second derivative. So here's what we're going to end up with. The derivative of 2x with respect to x is 2. And then I'm going to add to that 8. Since that's a constant, I'm just going to copy it into my derivative. And then times the derivative of y dy dx. Now when we use implicit differentiation, we assume y is a function of x. And dy dx is also going to be a function of x. So this is a function of x times a function of x. So I'm going to apply the product rule. The first piece of my product is y. And the derivative of y with respect to x is dy dx. Times the original second piece of the product. So this is going to look a little bit goofy, but the derivative of y is dy dx, and the original second piece of my product, when I'm applying the product rule, is also dy dx. So I actually have dy dx times dy dx in that position, plus the original first piece of the product, which is y, and then the derivative of the second piece of the product. And the derivative of dy dx with respect to x is going to be our second derivative. So here's where the second derivative comes into play. So there's the derivative of the left side of the equation. The derivative on the right, we'll go ahead and do at this point too. So the derivative of 3y, since 3 is a constant, I'm just going to copy it into my derivative, and then the derivative of y with respect to x is dy dx once again. And then again, I'm going to copy that next 3 into my derivative since it's a constant, and then I'm going to have to multiply 3 by the derivative of x dy dx. Well, just like we did on the left side of the equation, x is a function of x times dy dx, which is also a function of x. So we're going to have another application of the product rule here. The derivative of x is 1 times the original second piece of the product, which is dy dx, and then plus the original first piece of the product, which is x, and then the derivative of dy dx, the derivative of the second piece of the product, is going to give you a second derivative. Now, it says find the value of the second derivative at point P found in part B. This would be much more challenging if it said to find the second derivative, because at this point we would now need to solve this for this expression, solve it for d squared y dx squared, or the second derivative of y with respect to x. It's possible to do that. It's going to get a little bit ugly, and you see that your answer is going to depend on the first derivative, which you have from part A, and you can put it in place of dy dx. Good news is we're not asked to do that. We're asked to find the value of the second derivative at this ordered pair. So what I'm going to do is I'm going to toss 3 in place of all my x's and 2 in place of all my y's. So that means I'm going to have a 2 in place of this y, and I'm going to have a 3 in place of this x over here. Now, This doesn't really get us very far because the thing that's appearing most often here is dy dx. Now if you remember from part B, dy dx was equal to a certain value at 3, 2. dy dx was equal to 0 at 3, 2. So what makes this very, very nice is that in place of every single dy dx, we can put a 0. So if we put 0 in place of this dy dx, 0 in place of this dy dx, I don't know what my second derivative is. That's what we're looking to solve for here. But then I can also put 0 in place of this dy dx and that dy dx. Either way, you're just going to get a 0 there in the end. And so now what you want to do is you want to solve this for the second derivative. So if you're looking to solve this for the second derivative, let's distribute to get rid of our grouping symbols. And I guess we don't really have to distribute, right? Because 8 times 0 is 0, so really I just have to do 8 times 2 dy dx. So I'm looking at 2, and then plus 8 times 2 gives me 16 times my second derivative. This piece is gone, this piece is gone, and then 3 times 3 second derivatives is going to give me 9 times my second derivative. And if I'm looking to find the value of the second derivative, now I just need to solve this equation for my second derivative. So I'm going to go across here since I'm running out of room at the bottom of the screen. I'm going to subtract 16 second derivatives from both sides. That's going to leave me with a 2 on the left side of the equation and negative 7 on the right. Right? 9 minus 16 takes you to negative 7. And then it looks like the value of my second derivative is going to be able to be found by undoing this multiplication. Divide both sides by negative 7, and you're going to end up with negative 2 over 7 as the value of the second derivative of y with respect to x. So here's the value of the second derivative at 3, 2. If you read this second question, it says, does the curve have a local max, a local min, or neither at the point P? So a local max on a curve would look like a point like this. A local minimum would look like a point like this. And a place that's neither a local max or a local min, but does have a slope of 0 would be like a cubic graph. So I kind of messed up my attempt at graphing a cubic there, but we have a horizontal tangent line here, and we have neither a peak or a valley at that point. If you look at the slopes of the tangent lines to this graph, we have steep positives. They become less and less steep as we progress across. Here's our 0 slope, and then the slopes become negative, more negative, more negative. So in this particular graph, at this point, the first derivative is 0, and the second derivative is negative. The reason why the second derivative is negative is because the rate of change of the slopes as you progress across this graph with tangent lines, you have steep positive slopes initially, smaller, smaller, smaller positive slope, right? You have a pretty steep positive slope here that I'm trying to draw, a more level positive slope, there's 0, and then the slopes become more and more negative. So the slope of the tangent line is decreasing as we progress across this graph. On this graph, the slope of the tangent line is actually increasing. You start off with a pretty big negative value, and then it gets less negative, 0, positive, more positive. So the second derivative would actually be positive on this graph, since the second derivative is the rate of change of the first derivative, and the slopes of the tangent lines are getting larger as we progress across this graph. Now, we don't really need to elaborate on this very much, because if you look at what we have down at the bottom of the screen from a few minutes ago, we knew that our second derivative was negative. Since the first derivative was 0 and the second derivative is negative at our ordered pair on this curve, we know that we're going to have a local maximum on that curve, since the slopes of the tangent lines are getting smaller as we go through that point where we have the 0 slope for the tangent line. We'll formally state this a little bit more later on in the year and develop some terminology to use with this, but that for now is how we'll have to answer part C.